Hello, fsharp. Welcome back. Took a week off because I had a cold, but that means this week is going to be double feature week. So each day I'm actually going to put out 2 videos instead of just 1 to make up for last week. And today what we are doing is we are continuing our journey of writing a optimized dictionary in just fsharp. Now, last time where we left off was we used the idea of Robin Hood hashing. And Robin Hood hashing is a way to resolve collisions. And you can find it here. If you go to Wikipedia, you can look up Robin Hood hashing, and I will include a link in the description of this video so you can go look at it. But basically the idea is that when 2 keys collide in the same bucket, we will then just search for an open bucket and insert that new key and value there in the array. And what it means is that, hey, if we go look for a key in a particular bucket and we don't find it, we might have to just search down the array until we do find it. And by using Robin Hood hashing, we're trying to minimize the distance a key could be away from its home bucket. Now, if we look at the performance results that we got from that, we see that our dictionary is currently faster than the .NET dictionary in every scenario. So we are faster for integers, for all different numbers of keys. We are faster than strings. Now, again, this is where I want to put my caveat, is that I chose this particular set of benchmarks for educational purposes. In the real set of tests that I did for saying whether a dictionary was better or not was much more extensive. So don't feel like this is all you would need to do, but this has been distilled for your education and your well-being. So the question is, can we go even faster? I mean, this is great, but there's always the desire for more speed. And this is again where I want to cite my sources. This entire thing was inspired by this talk by Malte, I think that's how you pronounce it, Skarupki, and I probably butchered the pronunciation of that, but this was a fantastic talk that was given at Cpp Con in 2018. And when I saw it, I'm like, that is fascinating. I wonder how many of these techniques I could bring to fsharp. And so that's what we've been doing this whole time. My whole trick is I don't actually do anything new or innovative. I see what people are doing in C and C++, and I just translate it to fsharp and present it to you. So I like to present my sources. Here's my source. So in his presentation, he's used all the techniques that we've used here so far. And now we're going to start to get to the final form. And that's the idea of a byte list. And he actually has a good blog post article where he describes this approach. He does cover it in the video as well, but there's kind of a more detailed blog post if you wanted to go into more of the details of it. Now, we aren't going to do a line-for-line copy of what he is doing. We are going to take inspiration from his approach and do it in fsharp. And I want to kind of describe how that's going to work for us. And he calls this a bytehell hash map, where bytehell is actually short for byte linked list. And so what is that? And you can see here, byte linked list. So let's go to the drawing board and describe how this works. And so, okay, I want that to cover all that space. Thank you. I want as big of a whiteboard as I can get. So here's the way it works. So again, we still have our backing array, and we are still going to possibly have collisions. So I'm just drawing some buckets in here. And so I have key 1 and it maps to here. So now I put key 1 inside this bucket. There's a value associated with this key as well. But for the purposes of kind of conserving the amount of space on this diagram, I'm going to omit the values, but just realize there are values associated with these keys because we are talking about a dictionary. So we have this key that's been inserted in this bucket. And let's say we have another key that would also map to this bucket. And before, what we have done is we've just searched down this array for an open space and inserted into it. And so, okay, we would search down and say, okay, is this available? And say like, okay, K2 goes here. And so K1, K2. Now, what happens when we go searching for K2, right? Right now, what we would do is K2 would still hash to the same bucket, we wouldn't find it because K1 is currently in this bucket. And so then we would start searching down the array. Previously, we would just have to keep searching the buckets until we came to a blank one. Like, hey, there's no key in this, so you need to stop searching. The key is not in this dictionary. Or like, hey, it didn't match, so you have to keep searching. But what would end up happening is, and I need to come back here a little bit. So in this case, we had K2 and it came in right after K1. But let's say we had some other keys in here. So we have K3 and we have K7, possibly all kinds of other things. And then K2. Then we come to insert K2. We try to put it in here. And we check here, it's not available. Check here, there's no space. And so K2 ends up being all the way down here. And so what would happen with our search that we would have to do is now we need to search for K2. We would still hash to this bucket, but now we have to go along like, hey, is K2 in here? No. Is it in here? No. Is it in here? Yes. And this searching is really inefficient. We would rather not have to check against the keys in all these buckets as we go along. It would be ideal if we were able to immediately go from look at K1 and say like, nope, K1 is not it. And then have some information that said, hey, where is the next key that hashed to this bucket? I don't want to have to search all these buckets. I would like to be able to just jump to it. And this is where the idea of the byte linked list comes in. So what we're going to do now is I'm going to undo this and we're going to change how these entries work. So previously, entries in here, entries in this bucket, what would an entry include? It would have the key, obviously. It would have the value associated with that key. We also stored the hash code so that we could very quickly and easily compare in case of like reference types. We don't want to have to go and like load the reference. We would just say, hey, do the hash codes match or not? And so we were storing the hash code value in the entry. Well, what would happen if we included an additional piece of information that was, let's call it kind of next. And let's say it is a byte. And what is this value? This value is the offset to the next key that also mapped to this bucket. So in the case of K1, what would this be? In the case of K1, next is equal to 1, 2, 3. So next has a value of 3. And so we're going to store this additional piece of information in this bucket saying, hey, when you come and compare K2 to this bucket, K2 hashes to this bucket. K1 is currently in here. That's the current key. So K1 and K2 are hashing to the same bucket. K1 got there first. When we went to insert K2, we kept track of how far away we were once we found a space for K2. And then we went back to this bucket and said, hey, guess what? Your next value is 3. And that's the offset saying the next key that hashed here is 3 buckets away. It's 3 entries away. And so now what we are doing is we're saying, hey, it's not here, but here's the next possible value. And so now when we go to look up for K2, we check against K1, it's not there, and say, okay, well, is there another key that mapped to this bucket, that hashed to this bucket? And if there's a value in next, if next is something other than 0, then we know, oh, okay, if you go 3 buckets down, that is another key that actually mapped to this bucket. And so what we do now, instead of having to check against K3 and K7 first, we can just jump to K2. And let's say we had another key. So let's say we had K9. And K9 also hashed to this bucket. Well, no space, no space, no space. Eventually you would come all the way down here. And so now what would happen is K2, this bucket, it would have a next equal to 1. Because K1 would have a next of 3, saying it's 3 buckets down. We would check this bucket. If we were checking for K9, we would go to K1 because it would still hash to K1. We check it, it's not there. We say, okay, there's another value. It's 3 buckets away. We come down here, check against K2. It's not K2, and K2 would have a next of 1. So now you go an additional bucket down. And what this is forming now is a type of linked list where we have that next is encoding a link to here, and then this has a value, a next value. This is the next is equal to 3, and this next is equal to 1. And so these next values are basically just offsets to the next value in the linked list. We are creating a linked list, but we're keeping all of the values in the array. And instead of the linked list, because before we did have the idea of like a linked list at the very beginning, where hey, we have an entry in here, but then that entry was to some linked list, and we had all the different elements, and they would have references to the different elements in the linked list. And we say like, hey, this is less than ideal because of cache issues. Like these values could be spread all over the heap, not necessarily on the same cache lines. And so we would go searching for these things. We are now, instead of encoding this linked list with references to other nodes, we are just encoding a linked list, except we are just doing offsets into the same array. We're saying, hey, how far away do you need to go in the array to find the next value that hashed to this bucket? And we're using bytes to do it because the probability of one of these values being over 256 buckets away is essentially 0. And it is small. So we're able to fit more data onto a single cache line. So we're embedding a linked list into the backing array using offsets to signify how much farther down the array do you need to go to find the next key that mapped to that bucket. So let's go look, well, let's talk about what the advantages of this are going to be. Huge advantage to this. You're not going to have to do all the comparisons to the intermediate keys. Now, those comparisons were fast because most of the time the hash codes not matching was enough, but you're still having to do much more work than you really wanted to. With having a linked list embedded in the array, A, you're still probably going to have very good cache locality, and B, you're skipping those intermediate checks and you're going right immediately to another key that you know hashed to the same bucket. So you're potentially eliminating a lot of work. This is fantastic. The code is a little complex though. So let's look at the code real quick and I'll talk you through it. So now we're going to the fast dictionary test project. We're going to the byte list and we're going to talk about what the logic is for inserting a value. And as you can see, it's a little intense. So here's the code for adding a struct entry. We have a hash code, we have the key, and we have the value. And let's compress this, and I'm going to talk you through it. So when we want to add a struct entry, we are starting with the hash code, the key, and the value. And the first thing we do is we compute the bucket that, I'm going to zoom in here a little bit just so it's nice and easy to read. We first compute the bucket that key hashes to by compute bucket index for that hash code. We then go look up that bucket, saying, okay, give me a reference to that bucket. If the bucket is available, life is easy. And we're just going to set the values for the bucket. Now, I created a separate function for just setting the values here. We can go ahead and look at it. But all it's doing is it's saying, hey, set these values to what we need them to be. And what's different here is you notice that I have this next field in my bucket now. I'm setting the hash code, I'm setting the key, I'm setting the value, which is all the same stuff that I did before, but now I am also setting that next value. If where was I? Okay. If it's available, and I've also encoded that the value that signifies that this element is the last element in a linked list, I set that as 0. So if this is the tail, this is the very end of the linked list, that next value will be 0 because the offset to the next element in the linked list is 0 buckets away because you're at it. So there's no farther to go. So that's why I had this next dot last value. It is a 0 byte saying, hey, you are at the end of the list. And we know that if that first bucket we go to, that first bucket we hash to, if that was available, we can insert our key and our value, and that this was the first element in the linked list that hashed to this bucket. If that bucket is not available, that means, well, first let's check that if the keys match. If the keys match, then we're just going to overwrite the value. Hey, if the hash code matches and the keys match, then we know that we are basically inserting a new value for that key. And so we're just going to overwrite the value. That's all we're doing here. And we do that by checking the hash code and checking that the keys match. If not, there's something in the bucket, the keys do not match. What do we do now? Now what we're going to do is we are going to ask, is this element that we're wanting to insert into, is this part of a tail from another linked list? Because if you remember from the diagram, we're like filling in values here. So when we wanted to insert K9, came in, it wasn't available. And we start searching for like, hey, where's an open spot for me to insert into? Actually, it would have been better if I said K2. Let's talk about K2. I wanted to insert K2. This spot was not available. So then I start searching and then I found this spot. What we're wanting to do though, when we're inserting, is we're checking, hey, I hashed to this bucket. This is my home bucket because I haven't gone through any loop yet to go searching for a new place to put this in. I am still at my home bucket. And if this current element is a tail from another chain, then what I'm going to do is saying like, hey, sorry, I hashed to this bucket. I need to be here. And you are part of a tail from something else. Like you're already away from home at this point. If what is currently in this bucket is a tail from another linked list, it is not at its home bucket. It is part of another thing's tail. So it's like, okay, sorry, you got to move out. I'm moving in because I hashed to this bucket. You didn't. And so I am taking over. So that's what's happening in this scenario. We're saying, okay, get out of here. We'll try to reinsert it. That's what the evict does. An evict, it pushes something out and then tries to reinsert. And then I'm going to set this bucket to this value that I just put in here. Okay. If it's none of those scenarios, this is what has happened. This is the K2 scenario. This is the K2 scenario. It is, and I'll go back to the diagram. We are now in the K2 scenario. K1 is the beginning of this linked list. K2 hashed to the same bucket. K2 said, hey, K1, are you part of a tail of another linked list? And K1 is like, no, I am where I am supposed to be. I am in my home bucket. And so K1 and K2 are now going to be part of the same linked list. So K2 is like, fine, K1, you are now the head of the linked list. I'm going to go find somewhere to insert myself into this array. So that's where this list search function happens. Okay, we're now going to search for, what we're going to do is we're going to go searching down the existing linked list. Let's go look at that code. Because, and this is why it's important, for K2, this is easy. When K2 comes in, K1 is the head of this list, and it's also the tail of the list, is the last element in this linked list. It's a single element linked list. And so what K2 is doing is it's saying, okay, K1, you're the head. I'm going to search down the linked list. Oh, K1, you are the end of the linked list. Because that's what this search does. It would say, it is checking, I need to get to the end of the existing linked list and then search for a space to insert myself. And so that is what this code is doing. Now, in the case of K2, it is the second element that's going into this linked list after K1. And so it then just immediately starts searching. I was slightly wrong when I talked about inserting K9. Because what K9 would do when it goes to insert, what its logic is, and I'm back to brush. So if K9 comes in, it says, hey, I want to insert into the same bucket as K1. K1 says, sorry, I'm home. I'm the head of this list. And K9 is like, fine, where's the next element in the list? And it comes down to K2. And then it says, okay, now I'm going to start searching for a spot to insert myself because it wants to be at the end of whatever list starts at this bucket. And so that's where this list search is coming in. It's like, hey, I need to search down. I need to get to the end of the list. Once I get to the end of the list, then I will start my linear search finding for the next place to insert myself. And so that's what this is doing. It's like, okay, look up the next bucket. Hey, am I inserting into the same linked list and do the keys match? If the keys match, and then I'm just going to overwrite the value. If it's not, then I'm asking, hey, is this the last element in the linked list? If it is the last element in the linked list, now I can just search for an empty bucket and insert myself. If it's not the last element, then what I need to do is I need to recursively call list search again, because I'm just basically going to keep going down the nodes in this linked list until I find the last element. Then I will search for that next empty spot. I apologize if this is confusing. It was a little complex to write. I'm not going to lie. I'll possibly in the future go back and like rewrite this and make it a little bit cleaner, but just the idea of embedding a linked list using offsets into an array, it's a slightly complex topic. It's not super straightforward. So yeah, there's an inherent amount of just complexity in this problem in dealing with edge cases. And so at the point it gets to the end of the list, it then calls this insert into next empty bucket function. So it's made it to the end of the linked list. And what it does is now it's just doing kind of like a linear search through the array looking for an opening. And once it finds an opening, then it's like, okay, I'm now inserting this new key in here and go back to that last element in our linked list. So in this case, at the point where like, hey, K9 finally found a spot, it inserted itself. It then goes back to the K2 bucket and says like, hey, your next value, that's now 1. To let this bucket know, like, you are no longer the end of this linked list because I've just inserted another key that hashed to the same bucket that was a part of this linked list. Whew. Okay, that got a little complex. But what does that mean for our searching now? So what happens if we want to go find a value? Well, fortunately, the logic for finding a value is not nearly as terrible. Because what we've done is we've just embedded a linked list into an array. So going and getting a value, now we're looking at get struct value. We get the hash code, we compute what bucket we're going to start at, and then we're going to start this loop. And what the loop does, it says like, okay, go get the bucket, check, do the keys match. If the keys match, return the value. Is this bucket the last bucket in this linked list? If it is the last bucket, we know we have searched through all of the buckets that belong to this linked list, and so raise this key not found exception. Otherwise, go look at the next bucket. You compute the next bucket index, and then you loop. You go back, and you're just like, hey, and what's really efficient about this is now, instead of having to iterate through all the intermediate buckets, we are just immediately jumping to the next key that hashed to that same original bucket. So we're potentially skipping a bunch of work. Well, we are skipping a bunch of work because we're only checking keys that we know hashed to that bucket. So eliminating a lot of work by being clever. And again, not my idea. This was Malte's. I'm taking it from him. He's, again, a fantastic talk. You should go watch it. But what does this do for our performance? Fantastic things. And just so you know, like, we're now kind of in our final form of what our dictionary is going to look like. We're now going to do like variations of this, but like this byte linked list is kind of like the final form. So we went from 54 microseconds down to 38 microseconds. This is great stuff. We went from 46 microseconds to 36. And if we're looking at strings, we're looking at 172 microseconds, 176, 252, down to 157, 164, and 234. So not as massive improvements on the string side, but that's because the string keys, you're dealing with a lot more cache hits, just because the strings can be spread out across the heap, and that's what's going on there. But performance improvements across the board, we are even faster than the .NET dictionary than we were before. So this is fantastic stuff. And believe it or not, we still have more we can do to improve this performance. So this is exciting. So I really appreciate you taking some time today with me to look at this. I am sorry if the explanations were confusing. I'm actually really exhausted. I did not sleep well this weekend, but I wanted to get this content out to you because it is just too exciting. And I'm really excited to kind of show you the variations that we're going to do on this to make it even faster. So thank you very much for spending some time with me. I really appreciate it. I hope you have a wonderful day. Bye-bye.